In this video, I'm going to show you one of the basic principles of physics, which is the principle behind technologies like transformers and generators and the kind of regenerative braking that we have in electric cars. I'm going to start off simple and then show you the full demonstration. And I'm also just going to show you what we observe first and ask you just to observe carefully what happens. And it's okay if you don't understand everything that's happening at the beginning, but we'll just figure it out together after you take your observations. So this first half of the setup is simply a 9-volt battery hooked up to this coil of wire. It's 3,400 turns of wire. And right now I haven't finished hooking up the circuit yet. When I do, you'll see an effect on this magnetic compass. So when I complete the circuit, current flows through the coils and the compass swivels almost 90 degrees and lines up with the axis of the coils. So you can see that there's a magnetic field being produced. And then if I break the circuit, the compass goes back to its original direction, which is the direction determined by the field of the Earth. Now I've got a second solenoid, which is hooked up to this old-fashioned analog voltmeter. And this is a whole separate circuit from this circuit. So I can slide this out. There's air in between there. There are no wired electrical connections between this circuit and this circuit. And I've still got the compass down in front where you can see it. And now I'm going to go ahead and complete the circuit as before. And while I do that, I want you to watch very carefully what happens on the voltmeter. So I'm completing the circuit now. The circuit's complete. You can see that the compass is still deflected. Now I'm going to break the circuit. Watch the meter. And now you can see that the compass is back to where it was. We've got these two coils. The primary one on the left and the secondary one on the right. And when we put a current through this one, it makes a magnetic field in the whole space surrounding it. And then what we measure as an effect on here with the voltmeter is evidence that there's an electric field being created in this space. So the cause and effect relationship here is that the magnetic field is creating an electric field. Let's simplify this a little bit. Let's just pretend that each of these coils only had one loop of wire. That just makes things a little bit simpler. And by looking at the compass, I was able to tell that the magnetic field made by this coil was to the left. So since I'm going to want to graph some things, I need to pick a coordinate system and say which way is positive, which way is negative. Just for convenience, I'm going to say that that way is the positive x-axis. So if I look at how these things are changing over time, I'm just going to come at this as if I'm the first person ever to see this effect and I'm trying to figure out what's going on. I can graph the magnetic field as a function of time. And it's 0 for a while. Then in the coordinate system that I've picked, it becomes positive and stays constant for a while. And then when I unplug the plug and break the circuit, it goes back down to 0. If you watch very carefully on the video, I think you can see that the voltage we measure on this coil, which is a measure of how much electric field there is over here, was not the same graph as that. You would kind of think that if it was the magnetic field creating the electric field, then this one would just kind of mimic that one, but with different units or something. But it's not that. What we actually saw was that the electric field first was 0, then at the instant when I plugged in the circuit and the magnetic field sprang into existence, I got a twitch on the needle in the negative direction. Then during this period in here, where the magnetic field was constant, even though there was a big strong magnetic field, there was no effect on the needle on the right. So the electric field was 0 for a while. And then I wanted to look carefully at the needle at the moment when I unplugged the wire and the magnetic field collapsed. At that instant, the electric field popped up, the needle went to the right. Now if we look at these two graphs and try to figure out what the relationship is between them, one thing we can see is that whenever the magnetic field is constant, we get 0. Constant value, even though it's a non-zero constant value, 0 effect. Constant, 0. It's only when the magnetic field is changing from one value to another that we get an electric field. That's how a derivative acts. So if we were the first person in the world ever to see this, we would say, well, something about the time derivative of the magnetic field is what creates this electric field. And the other thing we could say is that this electric field is an electric field that can push an electron around a loop. So it's a curly electric field, like water swirling as it goes down the drain, that kind of curly idea. So the way we write this in fancy vector calculus notation, which you actually don't have to know too much about to understand this video, is this. We say that the curl of the electric field depends on minus the time derivative of the magnetic field. And the minus sign tells us what is the direction of the effect. I've set things up so that that minus sign gives us this. So when this derivative is big and positive, because that slope is very steep and positive, we get a negative electric field, and vice versa. It actually depends on how exactly I hooked up the wires in the video, what I'll actually measure on the needle. Now this is a law of physics that applies separately to every single little piece of the universe. So this is really the way we think the laws of physics work. They're local laws of physics. So it's kind of this vision of the God who is just the ultimate nitpicker, who just focuses on one little tiny thing and just applies that law there, and then also takes care of other parts of the universe, every point in the universe, separately from everything else. And so if we look at our actual experiment here, here's a smaller coil similar to the big ones I used in the demonstration. We have, let's say this is the secondary coil, which is the one that's the one sensing the electric field. Then at every different point in space, all back and forth and up and down and in and out along this coil, that equation is happening. And then it's not super obvious how to apply that to the whole coil. I can simplify a little bit. I drew those coils in a simplified way as if they only had one loop, so I could say, okay, maybe that helps a little bit with simplifying things. But I've still got all the different points in space. There's a different, if this is the secondary coil, the primary coil over here is the one making the magnetic field. This one is getting some effect. There's an effect here, and there's an effect here, and there's an effect here. They're all different effects, all throughout the interior of this loop and on the wire itself and so on. So this doesn't directly help us to figure out how much of an effect we're going to see when we hook up this to our meter. And all we can kind of say is, well, maybe there would be some kind of averaging, but averaging over what? That's not totally obvious or trivial to figure out. But it turns out there is a surprisingly easy way to figure this out. It was figured out by a person named Stokes in the 19th century. And so there's something called Stokes' theorem, which tells you how to do the right averaging. And the result comes out fairly simple. So the result is that if you measure the voltage going around some loop like this, which is a measure of how much curliness of the electric field there is kind of in that whole region. That equals the time derivative of the magnetic flux going through that loop. And so that since the flux is sort of the total amount of magnetic field going through a certain area, what that tells us is that the right kind of averaging is some kind of area-weighted averaging. We're averaging over the interior of this loop, which has some area. And it's not what I would have expected, because I'm not as smart as Mr. Stokes apparently was. I would have suspected it would be some kind of volume averaging, but it's not. It's an average over area. This is known as Faraday's law. This is the differential form of Faraday's law. This is the integral form of Faraday's law. And it's a very important basic law of physics, and it's also the basis for a lot of important technologies, as I mentioned at the beginning of the video. This is a fun demonstration of induced electric fields. The basic physics principle here is that a changing magnetic field makes a curly electric field. So I've got these two pipes. This one's plastic and this one's aluminum. And I've got this magnet here. So the magnet sticks to the steel post. And I've got one end of the magnet labeled blue and the other pole labeled white. But aluminum is a non-magnetic material, so the magnet won't stick to the aluminum. So if I orient the magnet this way with the white side up and drop it into the plastic tube, it drops right through, as you expect. But if I stick it in the aluminum tube, it takes quite a long time to follow through. So the explanation of this is that a changing magnetic field creates a curly electric field. So as the magnet is dropping through the pipe, that curly electric field is sending currents swirling around through the aluminum pipe. And then the easy way to understand what effect that would have is from conservation of energy. As the current goes through a conductor, this is a conductor with a low resistance, so it's basically a short circuit, you're going to make a lot of heat. That heat has to come from somewhere by conservation of energy. So it comes out of the gravitational potential energy that the magnet is losing. So normally if I drop a magnet like this, the gravitational potential energy goes into the kinetic energy of the magnet and it speeds up. But if it's inside the pipe, all that gravitational potential energy gets used up in heating the pipe. I want you to stop and think about this next thing for a second, and then see if you make a correct prediction if I change something. So far, I've had the magnet white side up. Now I'm going to flip it, so the polarity is reversed. So now I want you to pause the video a second and think what should happen now if I drop it through the aluminum pipe like that. And don't just guess, try to think of a valid physics explanation of why that should be. Okay, so let's go ahead and do it. And the results are the same as before. So oriented this way, we get a slowdown. Oriented this way, we don't get a speed up. We do get a slowdown still. And the other fun thing to think about is this. This one's kind of harder. We were doing this all in the frame of reference of the lab. And in that frame of reference, the pipe is standing still, but the magnet is moving. So another thing to think about and try to figure out is, what about the frame of reference of a little ladybug riding this elevator down through the tube? In the bug's frame, the magnet is at rest and the pipe is moving. And so the same explanation is not going to work, and yet the bug observes the same braking effect. So we have to come up with some different braking effect, some different explanation to explain the braking effect. And in fact, this was something that bugged Albert Einstein when he was about 20 or 22. he understood both explanations, but he felt like they were too different, and the same phenomenon should not have two totally different explanations, just depending on what frame of reference you were in. And this was actually one of the thoughts that he led off with in the very first part of his 1905 paper, where he figured out the theory of special relativity.